Hello everyone, I'm Professor Sagar Dhotare. Today we are going to discuss about the design of cam and follower. So initially we will discuss few PhD pages for a reference purpose. So from PhD page number 7.110, the design of cam has been started. Here different type of curves, that is a simple harmonic, circular arc, double harmonic, cycloid, parabolic, cube number 1, constant pulse, cube or constant pulse 2, then 2 polynomial, 3, 4, 5 polynomial. So such kind of curves are used for design a cam. For that, whatever the equation of displacement, velocity and acceleration that can be given in PhD page number 7.110. In PhD page number 7.111, a few equations as well as the polydial cams has been given. Equations is written over here. Then characteristic equation for polynomial cams also given. In PhD page number 7.112, the comparison of various types of cam curves are shown here by based on velocity factor, acceleration factor, jerk factor, then cam speed application, performance at high speed, and basically uh, small comment. Okay, so here the material combined for cam and follower also shown over here. So normally for good combinations are Ci and phosphor bronze, hardened steel and phosphor bronze, Ci and softened steel. Then we have another combination, hardened steel and Ci. And what about the poor combinations of the material, that is a hardened steel and hardened bronze? If we are using two hardened material or two softer material, or one is too much soft and second one is too much hard, then the friction will be more, and because of that the wear and tear of the materials are get increase. That's why they have categorized good material combinations and poor material combinations. In PhD page number 113, the basic diagram has been shown, which we have already seen in previous lecture. The base circle diameter, pressure angle, cam profile, prime circle, pitch curve, direction of motion, then follower, trace point, all these things has been shown here. Also, they have given the displacement time diagram and the nomenclatures with respect to them. In next page, they given some factors related to cam and cam curvature equations. In PhD page number 115, the roller follower cam profile concave profile equation is given. Okay, contact stress equation is given. Also, they have provided the contact stresses values for cam material with two conditions, with no slide condition and having few slide condition. Okay, so for each and every, that is a example of gray cast iron, the hardness is 140 to 160 hp. If you consider a design contact stress, that is sigma c up to 4000, and if you consider sliding, then it reduces to 3600 kgf per cm square. Okay, similarly for different material it have provided. Now next one, the forces on radial cam with the reciprocating roller follower equations are given. We need to use this in our design also. Then maximum torque required to drive a cam, it is also equation is given, mt is equal to pv divided by omega. Then few displacement ratios by based on the cam angle, that correction factors are given over here. then circular arc cam with roller follower. Here the arrangement of the different followers with the cam profile. First one is a flat follower, second one is a tangent cam with roller follower, and circular arc cam with the roller follower. Now, these are the up to the 7.119. The design of the equations or the standard data for related to the cam has been shown in PSG. We need also data for design of a spring of follower. Then referring PSG page number 7.100, that is 100, you can get the equations for helical spin, that is circular section or rectangle sections. Okay, so the various equations and standard data is available based on the spring design till PSG page number 7.105. So that much PSG important pages are required for design of cam. Okay, so let's start the design with a simple example. A rotary cam with a central translatory roller follower has a forward stroke of 20 mm in 100 degrees at cam rotation with the simple harmonic motion, with a dwell of 40 degree, return stroke of 120 degree of cam rotation with SHM, and remaining dwell to complete the cycle. The mass of follower is 1 kg and the camshaft speed is 500 rpm. If the external force during forward stroke is 500 Newton and during return stroke it's 100 Newton, design a cam. Second, follower with the pin and spring, and third one is a camshaft. So what we have to design? Cam, follower with the pin and spring, and third one is a camshaft. So first of all, note down the given data. Stroke, which is given as a 20 mm, it is denoted by small h. Theta 0, it is the cam rotation at initial, that is 100 degrees centigrade. Also we can denote it over the we have already denoted with the theta 0, that is a, and next one theta d, that is a dwell 40 degree which is given, and theta r, that is a return stroke. Okay, so first we have considered as an outward stroke, then dwell, then return stroke. M is the mass 1 kg, n is equal to 500 rpm, that is the speed. Initially the angles we have converted into the radian for further calculation. The maximum pressure applied, that is a P max, it is nothing a maximum external pressure acting on the follower is 500 Newton, and minimum pressure acting on the follower is external pressure is 100 Newton. So first of all we need to take some basic assumptions. So basic assumptions, that is nothing but we are assuming a base circle radius which is not provided in a problem. So RB is the radius of base circle. I have considered RB is equal to 30 mm, and the radius of roller follower is equal to RF is equal to 7.5 mm. About the selection of material, referring page number 7.115, suitable material for cam and follower is 14 CR 1 MO 28 with contact stress, that is sigma C is equal to 1100 Newton per mm square. Considering sliding, because in a high speed there is a possibility of sliding as well as rolling, so that's why we have considered the sliding action also. Now heat treated, so the strength is 270 to 300 HB. Also consider the cam face width is equal to 10 mm. Now next we have to draw a displacement diagram and cam profile diagram. So initially in a first this is a displacement diagram. So how we can draw a displacement diagram? So initially I have marked the height, that is a h is equal to 20 meter with the suitable scale. Then I have draw this hemispherical hemisphere, or you can say hemicircle, half circle. Okay, then again we need to draw this rectangle based on the angles. So for 360-degree with the suitable scale that I have considered, scale 10 degrees equal to 2 centimeter, and based on 20 degrees is equal to 1 centimeter, and I have converted the length into the degree into the length, and based on that I have prepared first theta 0, that is outward direction, outward stroke is 100 degree, then dual stroke, that is a 40 degree, and return stroke is 120 degree, and remaining stroke, that is remaining 100 degree, will be the dual. So here I have make equal number of parts of that hemicircle, 1 2 3 4 5 and 6. That is 180 divided by 6, so you get angle 30 degree. So in between, this is an angle of 30 degree, this is an angle of 30 degree. So similarly you can make the 6 divisions. Now here also, as the rise and fall are simple harmonic motion, we have to divide same the linear length into the what we can say 6 division. Okay, so I divided into 6 division, 1 2 3 4 5 6. Okay, from this point I have drawn parallel lines to the axis, parallel lines to axis. Then these are the vertical lines. Okay, so that I have directly get few points. So here I get point A, then point B, point C, point D, point E, and finally it's point F. Okay, so based on these points, I'm create a curve or draw a smooth curve. Okay, so similar manner we have to create for returning stroke, as it's also a simple harmonic motion. Okay, so similar fashion you can create the total displacement diagram. Now how to draw? Now how to draw cam profile? Now these dimensions are very important, whichever we have calculated based on these points. So this distance 0 1 to A, 2 to B, 3 to C, 4 to D, and so on. So here initially we have to draw a base circle by giving the diameter by with respect to the diameter of 20, radius of 20, radius of 30 mm, which is we have already assumed at the initial stage. Now second, we have to draw another circle by considering the roller diameter, that is a tracing circle, or based on that you can find out the cam profile. Okay, so adding adding 7.5 in the radius dimensions, what do we get? 37.5 as a radius and drawn second circle. Here I have drawn second circle, that is a center arc circle. Okay, now next, how to prepare a profile. Okay, as we know that first 100 degree is simple harmonic motion. So first of all, mark, this is a start point. This is a start point. From this I have take a line of 100 degree. तो ये हो गया मेरा 100 degree का line. Now I have divided into the 6 segments by using 30 degree angle. Sorry, 100 divided by 3. Sorry, 100 divided by 6. Okay, so based on this, we can calculate the division angle. That is 33 degree point, 33.33 degree each. Sorry, extremely sorry. It's 16.66 degree. So according to according to that, I have plotted all the angles and marked over here. Now from this circle, we need to plot, or we need to take a radius of 1 to A and mark first point plus 15, then 2.5, then from point 1 you can mark this first point, then consider a radius of 2 to B. From this point you can mark the second point. This is the radius. Okay, this is a radius 2 to B, it's 2 to A, then it's 3 to C, it's 3 to 4 to D, then 5 to E, and 6 to F. Okay, so similarly, sorry, 5 to E and 6 to F. So similarly, you can find out the length. Okay, so this arc has been these points we can get from the distances which we have drawn from displacement diagram. Okay, so similarly आप लोग यहाँ पे वो arc point out कर सकते हैं, और based on that you can make a smooth profile. तो ये हो गया अपना first profile. Now second dwell is there 40 degree angle का, तो आपका ये second profile point तो same ही रहेगा 6 का. Now next, based on the returning process, similarly you have to consider 7, a 7J distance, then 6J distance, then 7H, 8I, 9J, 10K, 11L, and 12M. So you get this profile. Okay, and this remaining portion, this total remaining portion is a dwell. Okay, which is not mentioned over here. So similar fashion, you can easily draw the cam profile. Third step, we need to calculate the maximum acceleration force which is acting on the follower. The angular speed of the camshaft, which is calculated, that is omega is equal to 2 pi n by 60. The speed of rotation is 500. So omega is equal to 52.36 radian per second. Now maximum acceleration of the follower during the forward stroke for simple harmonic motion, the equation is given a0 plus minus pi square divided by theta 0 square into h by 2 into omega, where theta 0 is rising angle, it should be in a radian, एंगल में हमें वो डिग्री में दिया है. सो इनिशियली जब गिवन डेटा मिला था तभी हमने उसको रेडियन में कन्वर्जन किया था, so that we can use here directly. Okay, so you can put the value. H is 20 mm, then omega is 52.36. So putting all the values, what we get? A0, that is a maximum uh, forward stroke, maximum acceleration during forward stroke is plus minus 88.87 into 10 raised to 3 mm per second square. Next one, maximum acceleration of follower during return stroke. So similarly, the equation has been changed, only the angle get changed. Okay, पहले हम लोगों ने फॉरवर्ड के लिए किया कैलकुलेट किया था, अभी रिटर्न के लिए कैलकुलेट करेंगे. सो in this equation only theta 0 will be changed as a theta r. Okay, so putting all the values, what we get, the maximum acceleration for a return stroke is plus minus 61.68.5 into 10 raised to 3 mm per second square. So if you compare forward and return stroke, the maximum acceleration is always towards the forward stroke. Hence the maximum acceleration we need to consider, that is 88.827 into 10 raised to 3 meter per second square, or A is equal to 88.827 meter per second square. Fourth step, calculation of pressure angle. Okay, in this case of SHM, when the acceleration is maximum, then at that time the velocity is 0. Hence theta is equal to theta 0. The displacement of follower, that is y, is equal to h, and it is nothing but 20 mm. The distance between center of cam and center of roller follower, that we have what we can say denoted by capital R. That capital R is nothing but radius rp plus y, where rp is equal to rb plus rf, that is base circle radius, plus follower radius, roller forward radius. So addition of that, you can get a radius of center of cam. Okay, so total R, the value of capital R, what that is the distance between center of cam and the center of roller follower, that is a 30 plus 7.5 plus 20. So total is 57.5. The velocity of follower, as we know, that is 0, as we consider O at the top, that is when acceleration is maximum, the velocity is 0. The acceleration of that follower, maximum acceleration of the follower A is equal to minus 88.827, because it lies when we draw the force diagram. At that time the value of because the forces are positive and negative also, and because of that when we observe the maximum jerk, that is a P0, which will start from the bottom section, that we can say a negative section, and increases with the positive section. Okay, when we look at the jerk versus angular movement or theta at that in those diagram, and because of that the maximum jerk or maximum acceleration with multiplied by radius, so that we can get a jerk, and that will be a maximum, and which is as it is a opposite in opposite in sign, that's why it is in a below the line of action. Okay, so that's why the negative sign is indicated over here. Now next one, calculation of pressure angle. Pressure angle alpha is equal to tan inverse of V divided by R into W. So velocity is 0, so tan inverse of 0 is nothing but the pressure angle is 0. Next one, calculation of maximum follower forces. The maximum follower forces is nothing but the maximum external force acting on the follower plus weight of follower plus inertia force of follower, that is a P max plus M into G, that is a weight of follower, and maximum force or inertia force on follower, that is a M into A0. Okay, so putting all the values, what we get, the maximum force acting on the follower is 598.637 Newton. Next step, calculation of minimum follower force. So similarly, the minimum force acting on the follower plus weight of follower plus inertia of follower. So minimum force is 100 Newton. Putting remaining values, what we get, the minimum force is 171.495 Newton. Now next, to calculate the maximum cam force. So to calculate the maximum cam force, same equation we have already seen in PRG. Fn is equal to F max divided by cos of alpha minus mu 2a plus b divided by b into sine of alpha. As we know that the alpha is equal to 0 and we don't have the values of other things because it is multiplied. We know that we don't have any value of ab, but it is multiplied with the sine 0. Sine 0 is equal to 0. So the term get directly converted into the 0. Cos 0 is equal to 1. So what the maximum force or calculating a maximum force on cam is 598.637 Newton. Calculation of radius of curvature of cam surface. As we know that the pressure angle is 0, the maximum force acting is maximum acceleration, that is a minus 88.827 meter per second square, velocity is 0 meter per second. Then y displacement is equal to 20 mm. Then value of rp, we have already known that rb plus rf is equal to 37.5. Then the equation for calculation of radius of curve is equal to rp plus y bracket square plus v divided by omega bracket square, the whole bracket raised to 3 by 2 divided by rp plus y bracket square plus twice vw bracket square minus rp plus y into alpha divided by omega square. So here we all values are known. Putting all the values, what we get, rc is equal to 36.77 mm. So we have calculated the curvature radius. Next, the calculation of contact stress between cam and follower. Now here, whatever the material we have selected, the value for that contact stress is 1100 Newton per mm square. Equation for calculating the contact stress, sigma c is equal to 189.8 into square root of Fn by B into 1 upon Rc plus 1 upon Rf. Putting all the values, what we get, the calculated value, or after the calculation, the contact stress value what we get is 588.38, and which is very less than the design value. Hence our design is safe for pitting failure. Step number 9, the design of follower rod. The stresses induced in a follower rod are compressive stresses. Material considered is a plain carbon steel, that is a 55C8. Yield stress is 400 Newton per mm square. Factor of safety considered is a 5. So calculating the value of sigma c is equal to sigma yt divided by FOS. So what we get, design sigma c is equal to 80 Newton per mm square. So stress is equal to force divided by area, or load divided by area. So sigma c is equal to F max divided by pi by 4 dr square. So here the radius of the rod diameter of the rod has considered as a for compressive stresses. So it putting all the values and calculating the value of diameter of the rod is equal to 3.08. Now we have to modify that diameter up to 4. Next one, design of roller pin. Consider same material as we have considered above, that is a plain carbon steel with value of sigma t yt is equal to 400 Newton per square Newton per mm square. FOS, that is a factor of safety, is 5. Then crushing stress is equal to 80 Newton per mm square. Tau is equal to 0.5 times of crushing, so it's a half of crushing stress, so tau is equal to 40 Newton per mm square. So design of roller pin is based on two constraints. First, design of roller pin based on the direct double shear failure, that is Fn is equal to twice area into tau, that is a pi by dp square divided by 4. Okay, so putting all the values, what we get, the value of dp is equal to 3.18 mm, modified value is 3 mm. And second one, the design of roller pin based on the crushing failure. Here the area is length into the diameter, that is a crushing area. So Fn is equal to Lp dp into sigma cr. The empirical relation we have considered between length and diameter of pin is Lp is equal to 1.25 times of dp. So putting all the values, and what we get, the dp is equal to 2.44 mm, which is again equals to near about 2. dp is equal to 3 mm. From both the comparison, what we get, that is a value of dp is 3. If anyone having a larger value, that value we can select. Okay, so as the dp is equal to 3, the length of pin is equal to 3.75 mm. Now next step is the design of spring. Okay, so for design of spring, we need to refer PhD page number 7.100 to 7.105. Design material of the spring should be oil hardened and tempered with the plain carbon steel wire grade VW with the sigma U is equal to 1380 Newton per mm square, referring PhD page number 7.105. Modify modulus of rigidity of the spring material, that is a G, is equal to 79.3 Newton meter square. And consider the spring index C is equal to 8. Generally it is considered in between 2 to 10. Factor of safety considered as a 1.5. The spring is subjected to continuous fluctuating stresses, therefore it is designed for a fatigue load using the modified Soderberg diagram, which is shown in PhD page number 7.102. So the calculation of mean load PM is equal to maximum load plus minimum load divided by 2. So mean load is equal to 385.07 Newton. Then amplitude load PA, it is nothing but maximum minus minimum force divided by 2. PA is equal to 213.57 Newton. The design of spring for related repeated load, referring PhD page number equation from PhD page number 7.102, tau A is equal to 8 Ks PD PA into D divided by pi into D cube, where small d is the diameter and capital D is a spring index, outer diameter of the spring. So here Ks is a wall stress factor, which is referring PhD page number 7.100. Ks is equal to 4C minus 1 divided by 4C minus 4 plus 0.615 divided by C. So putting value of C is equal to 8, Ks is equal to 1.184. Tau A is equal to there are two unknown parameters now, tau A and D. So we can get an equation tau A is equal to 5151.36 divided by D square, which is in Newton per mm square. Now secondly, tau M. Okay, calculating the tau M. Tau M is nothing but mean shear stress. So that can be calculated referring page number 7.102. Tau M is equal to 8 into KSH, that is direct shear stress, into PM mean load, into C divided by pi by D square. So putting all the values, first of all we need to calculate KS is equal KSH is equal to KS is equal to KSH into KC. So KC is nothing but a curvature factor, which is we can find out from PSG, that is 7.102, 1.11, and KS is equal to 1.184, which we have already calculated. So KSH is equal to 1.066. Putting these values into the tau m's equation, what we get? Tau m is equal to 8362.32 divided by D square. So yield strength in a shear for spring wire psi m is equal to tau m is equal to 0.5 times of sigma u. So 0.5 into 1380, tau m is equal to, that is a yield strength of the shear spring, is equal to 690 Newton per mm square. Similarly, you can calculate the endurance strength by referring page number 7.102. Tau 0 is equal to, that is a shear stress for endurance or repeated load, that is 0.263 sigma u, that is 362.94 Newton per mm square. Now calculating or determine the spring diameter during the equation using following equation, that is 1 upon n is equal to tau m minus tau a divided by tau y plus 2 into tau a divided by tau 0, referring page number 7.102. So putting all the values and properly calculating the diameter of the spring, D is equal to 7.03. So modified it to D is equal to 8 mm. So capital D, that is a mean coil diameter, capital D is equal to C into D. So it is 64 mm. Now number of active coils we need to calculate, that Q is equal to GD divided by 8 C cube into N. So Q is nothing but a spring rate, or you can say stiffness. So how we can calculate stiffness? That is a load divided by deflection. So maximum load divided by minus by minimum load divided by deflection. That deflection is nothing but 20 mm. That is called as a stroke. So putting all the values, what we get? Q is equal to 21.357 Newton per mm square. So now using equation Q is equal to GT divided by 8C cube into N, page number 7.100. Putting all the values, what we get? We get N is equal to, number of tons are is equal to 7.25, approximately 7.5 tons are active, prolly active. Next one, design of camshaft. Okay. In simple harmonic motion, the maximum velocity of out we can calculate with the equation V is equal to pi hm divided by theta 0 to into omega. So putting out the values, what we get? The velocity is equal to 0.942 meter per second. Now input power to the cam and follower mechanism, P is equal to F max into the velocity. That F max is equal to 598.637 into the velocity, that 0.942. So maximum input power which is required for drive cam and mechanism is 564.2 watt, that is a 0.5642 kilowatt. Considering the mechanical efficiency of cam and follower is 90%, the input power to the cam P input is equal to power required to drive the cam divided by total efficiency. So the input power is equal to P divided by maximum efficiency of mechanical efficiency. So putting all the values, what we get, the input power required to drive a camshaft is equal to 626.9 watt, that is 0.6269 kilowatt. For Pi is equal to, now what we need to calculate, we need to calculate a torque so that we can easily design a shaft. So input power is equal to torque into the angular velocity. Putting all over the values, what we get, the torque is equal to 11.97 Newton per Newton meter. So now for design of shaft, we have selected the material, that is medium carbon steel 45C8 with the stresses sigma u 670 Newton per mm square and yield stress 360 Newton per mm square. According to the ASME code, tau is equal to 0.75 into 0.18 times of sigma u. So calculating the value of tau based on the value of sigma u is 90.45 Newton per mm square. Okay, with respect to the L stress, the equation is 0.75 into 0.3 into sigma y. So what we get, that is a tau is equal to 81 Newton per mm square. Now from these two equations or two values, we have to select a smaller value. Then and then only we get a safer dimension of the shaft. So selecting 81 Newton per mm square. We know that the shear stress tau is equal to 16 kT into torque divided by pi d cube. Okay, so pi by 16 into torque is equal to pi by 16 d cube into kt into that torque is equal to tau into pi by 16 d cube. So that is the equation. Now kt is the combined shock and fatigue factor for torsion, which we have considered as a 1.5. Putting all the values of torque, then tau, kt, what we get, the diameter of the shaft is 10.41 mm. We can modify that value up to the 12. Okay, so similarly you can again putting the value of diameter and you can calculate the value of tau. So this is the simple method, or these are the some steps which we can use for design of any cam and follower by simple harmonic motion. Okay, so in next lecture we will discuss with the rotary disc of cam with a center translatory roller follower having cycloidal as well as cycloidal forward motion and simple harmonic return motion. Okay, so in the next lecture we will discuss about the other type of motions. Okay, so thank you very much for joining this lecture.